Yesterday we have studied about the postulates of VSEPR theory. That is, we have studied that according to this theory, the geometry and the shape of the molecule will be decided by the electrons present in the valence shell of the central atom. And we have seen that since this electron cloud carry negative charge, they will be having a repulsive interaction. The third postulate we have seen that in order to minimize this repulsive interaction, they should be arranged in such a way that the distance between them is maximum. Then the last postulate we have seen that the magnitude of repulsive interaction varies in the order lone pair repulsion is stronger than lone pair bond pair repulsion, which is stronger than bond pair repulsion. Today children, first let us see the shape or the geometry of some molecules with central ion having lone pair of electrodes. Is it clear? Today at first we are going to see the shape or geometry of some molecules with central ion with lone pair of electrodes. Suppose if you consider the type of molecule is AB2E, where A is the central element, B2 represents the bond pairs and E represents the lone pairs. That means in this particular type of molecule, you can see the presence of two bond pairs and one lone pair. Is it clear? I have shown here two bond pairs, one lone pair. Then this will be the arrangement of electron pair. You can see that one lone pair is there which is arranged towards the top. And here just see the molecule possesses a bell shape. Example we can consider sulfur dioxide. Is it clear children? Suppose if the type of the molecule is AB2E, that means the compound in which the central atom possesses two bond pairs and one lone pair, the arrangement of electron pair will be this way. So the shape of the molecule is bent and we can see a simple example as sulfur dioxide. Okay. Second example, let us consider the type of the molecule as AB3E. That means what is it? Three bond pairs and one lone pair. So this type of molecule possesses three bond pairs and one lone pair. So the arrangement will be like this. Just say it has a pyramidal like shape with a lone pair. So we can see that the structure, the shape of the molecule is trigonal pyramidal, and ammonia is a simple example for this. This ammonia will be having this lone pair of electrons over here. In all these cases, you can see the presence of lone pairs. Is it clear? If the molecule type is of AB3E, that means if it possesses three bond pairs and one lone pair, then the arrangement of electron pair will be this way and the shape of the molecule is trigonal pyramidal. Is it clear children? Next you consider if the molecular type is AB2E2. That means it has two bond pairs and two lone pairs. So here you can see that black dots are marked as the lone pairs. So just say two lone pairs and two bond pairs are there. Then the molecule will have a bell shape. Exactly same as the structure of water. Water is an example for bell-shaped molecule which possesses two bond pairs and two lone pairs. Next one you consider the type of molecule which possesses the formula AB4E. That means it has four bond pairs and one lone pair. Okay, the type of molecule is AB4E, which has four bond pairs and one lone pair. So one lone pair I mark this side and you can see the bond pairs arrangement. That means it possesses a seesaw geometry. You know that seesaw? So SF4 is an example for this particular type of molecule. Okay, next one let us consider if the type of molecule is AB3E2, means it is having three bond pairs and two lone pairs. Here you can see the presence of two lone pairs and just see the shape children. It has a T-shaped structure. So example we can consider it as ClF3 is an example for the type of molecule which possesses three bond pairs and two lone pairs. Next one you consider the type of molecule as AB5E. That means it has five bond pairs and one lone pair. So it possesses just one lone pair. You can see towards the bottom. I mark one lone pair and 5 bond pairs are there. So the structure or geometry of the molecule is square, pyramidal, and example we can consider BRF5 as an example. And the last one you consider, if the molecule is of the type AB4E2, it has 4 bond pairs and 2 lone pairs. Again children, just see towards the bottom and the top you can see the presence of lone pairs. Okay, towards the bottom as well as towards the top you can see the presence of lone pairs and 4 bond pairs are marked on both the sides. So the molecule possesses a square planar structure. XCF4 is an example for this. Is it clear children? I will explain it once more. That is, we are just explain the shape or geometry of molecules in which the central atom possesses some lone pair. If the molecule possesses the type AB2E, then that means it is having 2 bond pairs and 1 lone pair. We have seen that it has a bent structure. An example we can consider SO2. If it is of the type AB3E, that is 3 bond pairs and 1 lone pair. So the structure will be trigonal pyramidal in structure. And example we can consider ammonia. If the type is of AB2E2, that is it possesses 2 bond pairs and 2 lone pair, then the structure, the shape will be bent shape, and water is an example for this particular type of molecule. Next one you consider the type of molecule as AB4E, in which it has 4 bond pair and 1 lone pair. So the molecule, the geometry will be seesaw. An example we can consider it as SF4. Next one you consider AB3E2. That means the compound possesses 3 bond pairs and 2 lone pair. The geometry will be T-shaped, and the example we can consider it as ClF3. Next one you consider AB5E, where it has 5 bond pairs and 1 lone pair. So the geometry will be square, pyramidal, and example is BRF5. Or the last one you consider, if the molecule type is of AB4E2, that is it has 4 bond pairs and 2 lone pair, then it will be having a square planar structure, and the example is XCF4. Is it clear children? These are few cases where we can see that the central ion possesses some lone pairs. Now let us see the example for some compounds in which the central ion possesses only bond pairs. Okay, so let us consider the example for the compounds in which the central ion possesses only bond pairs. First case we have discussed about the structure or the molecular arrangement of molecules in which it is having the central ion is having lone pairs, and now we are going to see the geometry of the molecule in which the central ion possesses only bond pairs. Children, in this case we can see that, let us make a column, that is suppose you consider number of bond pairs. Then let us consider the shape and example. Okay, here we can see that suppose if the compound is having only 2 bond pairs, if it has only 2 bond pair, then the shape will be generally linear. It has a linear geometry. Example we can consider BeCl2. Okay, if it has only 2 bond pair, then the shape will be linear and it will be having the example we can consider it as BeCl2. Suppose if it has 3 bond pair, then the structure we can say that it will possesses a trigonal planar structure. It has a trigonal planar structure. We can consider example as BF3. Okay, if the element possesses 3 bond pairs, then we can say that the structure will be trigonal planar and the example is BF3. If it is having 4 bond pairs, then we can say that the example can be tetrahedron. The shape can be tetrahedron and the example we can consider it as CH4. If it has 5 lone pairs, then we can say that it has a shape of trigonal pyramidal structure. Trigonal pyramidal. An example we can consider it as PCl5. Or if it has 6 bond pairs, then we can say that the shape will be octahedral. And example we can consider it as SF6. Is it clear, children? Here I have given certain examples of molecules in which the central ion possesses only bond pairs. If it has 2 bond pairs, the structure will be linear. With 3, we can see trigonal planar structure. With 4, tetrahedral structure. With 5, trigonal bipyramidal structure. And with 6, we can say that it possesses an octahedral geometry. Is it clear, children? Before starting about valence bond theory, let me first explain few things which is left in case of VSEPR theory. Children, according to the last class video, we have seen that when the molecules possesses a shape in which the central atom is having lone pair of electron, the structure was slightly different from that particular structure in which the central atom was having only bond pairs. Actually, this is because of the presence of that lone pair of electrons. You know that according to VSEPR theory, we have studied that lone pair repulsion is stronger than lone pair bond pair repulsion, which is stronger than bond pair repulsion. So, according to the number of lone pairs present in the central atom or present in the molecule, the structure shows the difference. Is it clear, children? So, now let us start with valence bond theory. Actually, this theory was first put forward by Hitler and London. This theory was put forward by Hitler and London. If you consider it as Hitler and London. Okay, and some improvement in this case is done by Pauling. Even though it was put forward by Hitler and London, the improvement has been done by Pauling. So, in order to this theory, valence bond theory is otherwise termed as orbital concept theory. Is it clear? Valence bond theory is also termed as orbital concept theory. In order to explain this valence bond theory, first let us see the formation of hydrogen molecule. Okay, children, if you consider this hydrogen molecule, that is, it needs 435.8 kilojoules of energy to get decomposed to 2 hydrogen atoms. Is it clear? This hydrogen molecule will be using 435.8 kilojoules of energy. Hydrogen molecule will use, if you consider, hydrogen molecule will use 435.8 kilojoules of energy and just convert it to 2 hydrogen atoms. That means 1 mole of hydrogen needs 435.8 kilojoule of energy to get converted to hydrogen atom. Is it clear? That means in short we can say that the energy of hydrogen molecule is lower than the energy of hydrogen atom. And you know, children, as the energy decreases, the stability of the molecule increases. Is it clear? Here from this equation itself we can see that energy of hydrogen molecule is less than the energy of hydrogen atom. Now let us see how this process is going on. Children, you know the electronic configuration of hydrogen. Hydrogen possesses 1 electron in the 1s orbital. It has just 1 electron in 1s orbital. Now you consider 2 hydrogen atoms, that is the nucleus, which has Ha and Hb. Ha and Hb represents 2 nucleus of 2 hydrogen atoms A and B, and Ea and Eb represents the electrons in that. Here you know that between Ha and Ea, that is positive and negative charge, you can see the presence of attractive force. At the same time, you can see between Ea and Hb during the formation there will also be an attractive force. And between Ha and Eb also you can see the presence of attractive force, as well as between Eb and Hb you can see attractive force. Since you know that always opposite charges attract each other. But once this case happened, then you can see that between the electrons we can see the presence of repulsive force, and between the nucleus again repulsive force is there. Is it clear, children? The type of attractive force and repulsive force. You know, in the beginning, this magnitude of attractive force is stronger than the magnitude of repulsive force. Is it clear, this diagram? So we can say that the magnitude of attractive force is stronger than the magnitude of repulsive force. So what happens if you just consider these two hydrogen atoms? Since the magnitude of attractive force is stronger, they will be approaching each other, they will be coming close to each other, and finally they will be overlap to form a molecule. Is it clear? We can see that we know that the magnitude of attractive force is stronger than the magnitude of repulsive force. So it tends to bring the atoms together. Okay, it brings the atoms together, and at a particular distance, what happened after this? The magnitude of attractive force will be smaller than the magnitude of repulsive force. So further overlapping will not take place, and that is what students had shown with the help of this graph. Here you can see that two different atoms are there. This represents the approaching atoms, and here the overlapping takes place. They mingle together, and this particular distance where the attractive force just balances the repulsive force is termed as critical distance. Is it clear? This distance is termed as critical distance. The distance at which the attractive force just balances the repulsive force. After this, children, the magnitude of repulsive force will be stronger than attractive force. Is it clear? So this particular distance at which the attractive force, the magnitude of attractive force just balances the repulsive force is termed as critical distance, or we can say that this particular distance is also termed as bond length. About this bond parameters we will be studying in the next class. So this particular distance at which the magnitude of attractive force just balances the repulsive force is termed as critical distance, or it is also termed as bond length, or we can say that this is the point where the system possesses the least potential energy. That means maximum stable. This energy associated with this particular distance is termed as bond enthalpy. Is it clear? This energy is termed as bond enthalpy. That means at this particular point, system possesses the least energy and hence maximum stability. Is it clear, children? Explanation of the formation of hydrogen molecule. So from this we can prove that hydrogen molecule possesses less energy compared to hydrogen atom. That is why always hydrogen atom shows a tendency to combine together to form a molecule. Now this particular interpenetration of atomic orbitals. Here we have seen that the two atoms overlap each other. Actually this overlapping means it is the interpenetration of atomic orbitals. Is it clear? Interpenetration of atomic orbitals is termed as overlapping. So here at this particular distance, these two atoms overlap each other. And why further overlapping? That is, it overlaps like this only. Why it is not like this? Since after this particular point, what happened? The magnitude of repulsive interaction is more than, or it is stronger than that of attractive force. So further overlapping is not possible. Is it clear, children? And overlapping means it is the interpenetration of atomic orbitals is termed as overlapping. Is it clear? Formation of hydrogen molecule. Now let us study about types of overlapping. Now basically overlapping are of three types. First one is termed as positive overlapping. Positive overlapping means when the lobes, that is LOBs, when lobes having same sign when they interact, overlap each other, that results in the formation of positive overlapping. Is it clear? Positive overlapping means when lobes which is having same sign, they interpenetrate, that results in the formation of positive overlapping. So these are the different types of positive overlapping which can generally take place. Next one we can consider negative overlapping. Negative overlapping means when lobes which are having opposite sign. Okay, lobes which have opposite sign when they interpenetrate. That is, if you just consider here like this. One is negative and the other one is positive. When this type of overlapping takes place, then it is termed as negative overlapping. And the example you consider plus minus, and here it will be then plus and minus. So this type of overlapping in which lobes which have opposite sign takes place, then it results in the formation of negative overlapping. Here also it can be like this also. And again, if you consider they are having opposite sign, then again this overlapping is termed as negative overlapping. Is it clear? So in case of negative overlapping, the lobes will have opposite sign. Now the last type of overlapping we can consider it as zero overlapping. In case of zero overlapping, it implies that actually no overlapping takes place. Suppose if you draw two atomic orbitals, one is like this and the other one you consider over here. Now there is no overlapping between these atomic orbitals. This type of overlapping is termed as zero overlapping. Is it clear, children? So we have seen that when two lobes having same sign overlap each other, it is termed as positive overlapping. And when they are having opposite sign, when they interpenetrate each other, it results in the formation of negative overlapping. Is it clear? Children, even though we have started our class with covalent bond, valence bond theory, we didn't mention about the postulates of valence bond theory. So now let us study about the postulates of valence bond theory. Valence bond theory, we can consider it as VBT also. As I told you that this theory was first put forward by Haeckel and London. Okay, this theory was put forward by Haeckel and London, and further it was improved by Pauling. Okay, so valence bond theory is otherwise termed as VBT. Now the first postulate in this theory is that a covalent bond is formed by the overlapping of half-filled atomic orbitals. Is it clear? Of the central atom. A covalent bond, we can see that a covalent bond is formed by the overlapping of, overlapping of half-filled atomic orbitals. When half-filled atomic orbitals overlap each other, that results in the formation of a covalent bond. Second postulate, we can say that the electrons present in this half-filled atomic orbitals, will have opposite spin. They possesses opposite spin. Children, you must have studied about spin in second chapter. So I am just telling that now. Electrons present in half-filled orbitals will have opposite spin. The third postulate we mentioned about the strength of covalent bond. We can see that the strength of covalent bond actually depends on, extent of overlapping. Is it clear? The strength of covalent bond depends on extent of overlapping. That means it is very clear that suppose a bond is formed like this. Extent is very small, so you can break them very easily. But if the extent of overlapping is more, then it is difficult to break the bond. So as the extent of overlapping increases, strength of covalent bond also increases. Is it clear, children? I'll repeat again, once more I'll repeat the postulates of VBT, that is valence bond theory. The first postulate is that a covalent bond is formed by the overlapping of half-filled atomic orbitals of central atom. Second postulate is that electrons present in half-filled orbitals will have opposite spin. Okay, and the third postulate is that the strength of covalent bond depends on extent of overlapping. As the extent of overlapping increases, strength of bond also increases. Is it clear? Okay, now let us study about the different types of covalent bond. This covalent bond, basically we can divide it into two types, that is sigma bond and pi bond. Okay, covalent bond we are going to divide it into two types, sigma bond and pi bond. Is it clear, children? So first let us see what are the sigma and pi bond. When two atomic orbitals undergoes axial overlapping, okay, like this. So sigma bond is formed by the axial overlapping of two atomic orbitals. Okay, a sigma bond is formed by the axial overlapping of atomic orbitals. But a pi bond is formed by the sidewise overlapping of atomic orbitals. Is it clear how it is forming? It is formed by the sidewise overlapping of atomic orbitals. Second point we can see that a sigma bond can be formed between S orbital, or it can be formed between S and P orbital, or it can be formed between P and P orbital. Is it clear? These are all sigma bond. In this case, it is formed between P and P orbital, or between S and P orbital, and between S and S orbital. But a pi bond is formed only between P and P orbital. Is it clear? Here it results in the formation of a pi bond. So first we can see that it is formed by the axial overlapping of atomic orbital, and pi bond is formed by the sidewise overlapping of atomic orbital. Second, we have seen that sigma bond can be formed between SS, SP and PP bond orbitals, but a pi bond is always formed between only P orbitals. Third point, we can see that, you can see, just listen here, you can see that the extent of overlapping is more in case of sigma bond. Okay, so sigma bond is always stronger than pi bond. In this case, the extent of overlapping is less. Extent of overlapping is less, so pi bond is weaker compared to sigma bond. Now just see, sigma bond is formed along internuclear axis, so free rotation is possible here. You can rotate the sigma bond. There will not be any breaking process. But pi bond, since it is formed by the sidewise overlapping, if you rotate it, it will break. Is it clear, children? So third point, we have seen that since the extent of overlapping is more, sigma bond is stronger. In case of pi bond, the extent of overlapping is less, so it is weaker compared to sigma bond. Sigma bond free rotation is possible, but in pi bond free rotation is not possible. Is it clear? That is about the difference, some of the difference between sigma and pi bond. I will explain it once more. A sigma bond is formed by the axial overlapping of atomic orbitals, but a pi bond is formed by the sidewise overlapping of atomic orbital. Sigma bond can be formed between SS, SP and PP orbitals, but pi bond is always formed between only two P orbitals. Sigma bond extent of overlapping is more, hence it is stronger. Pi bond, the extent of overlapping is less, so it is weaker. Sigma bond free rotation is possible, but in pi bond free rotation is not possible. Is it clear, children, the difference between sigma and pi bond? That's all for today. The rest we'll study in next class.